Good afternoon, everybody. Welcome. So today we're going to continue our journey into AC circuits. So remind you what we did last lecture, that was Tuesday. We started describing very simple RC circuits where we were using a full-on AC description of a of the RC circuit. So we had this problem that if we had if we wanted to describe the response of that circuit in real time, we needed to solve a differential equation because, well, for the resistor we can use Ohm's law, R is V over I, solve for the current. The way that the voltage and the current relate for a capacitor are through an integral, because for capacitor it's Q over V, where Q is the integral over the current. So you very easily run into this issue with even the most simple of AC circuits, which I've seen many complicated circuits, and RC circuits are really they're the easiest ones that you'll find that are real AC circuits. Obviously DC, just resistors are also, strictly speaking, you can call them AC circuits, but that's cheating. That's like choosing not to play. So RC circuits, even with as simple a setup as that, we found that it was mathematically quite tedious. So we explored this concept called a phasor, and a phasor is this complex physical quantity that describes two things: the amplitude and the phase, and it does so with a complex number. And the real part of the phasor is the in phase part, and the imaginary part of the phasor is the out of phase part. And when you want to go from phasor form to real form, you have to plug in the time dependence. And that's one of the biggest advantages of doing phasors, is that you don't have to keep writing all the time dependencies. And the second thing is that you don't have to deal, because you don't do anything with trig, the cosines and sines, they're not there. You do everything in a complex space. You don't have to worry about trig identities. So if you have a circuit that is quite complicated, you can just add the voltage phasors or divide the voltage phasors, put the current phasors, and it's all complex arithmetic. And therefore there's no trig identities, and it's very easy to say, okay, the real part is going to be the sum of all the real phasor parts. And then it's very straightforward to calculate the response of a circuit. Now, this is a very powerful concept, but I know that complex numbers and complex physical quantities are always kind of a stumbling block for students because they haven't really seen it before. But there's a reason we use complex numbers, because it really does make life much easier. As much as I like complex numbers, I'm not doing it because it looks baroque and interesting. I'm doing this because it's the best way to solve these kind of problems. So trust me on this. The same way as when we started this class, back about 3 years ago, it feels like. So when we started this class, we went full on into vector mode. So we did not write vector components out anymore. We just had a position vector and we let it do stuff. We didn't split it up in vector components anymore because it's needlessly complicated. Also, it kind of hides the physics. So we're not doing it because it's complicated, but we're doing it because it's better. And so hang in there and study it. And we will see phasors again when we do electromagnetic waves. So when we do phasors, the one thing that we don't describe is the explicit time dependence. So you always need to assume that there's something that is going on that is sinusoidal in nature or cosinusoidal in nature. And we specify the frequency, and we do that on a separate piece of paper or at the introduction of some kind of a network problem. And then afterwards, when we do all our phasors, that frequency doesn't show up in the explicit time dependence, but the frequency does show up when we describe impedances. So impedance, for a resistor, the impedance is just a resistance. For a capacitor, the impedance is the voltage phasor over the current phasor. And we found that for a capacitor, the impedance is 1 over I omega C. So today, we will add the impedance of an inductor to it. And that one goes in the opposite direction, points in the positive I direction, whereas the capacitor points in the minus I direction. And the fact that the inductor and the capacitor points in opposite directions are actually super, super useful in circuits. So there are really lots of cool tricks that you can do. If you have a capacitor that you don't want, you just choose the right inductor and you put it either in front or in parallel. And you can, if you tune it right, you can basically make the capacitor go away. So the fact that they can kind of work against one another, and if you have one that you do not want and the other you do, or you have both and you want to tune it, those are really useful useful building blocks. Now, one more thing. So when we use phasors, we have this very neat way of describing time dependence or throwing time dependence out. And as a result, we don't have to do calculus anymore, but it becomes arithmetic. All right, so we just have numbers and physical quantities that we just add, divide, factor out. This is a big advantage of phasors, but I'm going to tell you another technique. It's Fourier analysis, and some of you have seen it already. But Fourier analysis is that thing that is this marvelous machinery. And there's also Laplace transforms where you can take a differential equation and you apply a Fourier transform to it, and then it becomes a polynomial. And now it's just a polynomial, which means it's just arithmetic and finding roots. You don't have to do any calculus anymore. So it's a beautiful piece of machinery if you have a chance to explore it. And just like phasors, just dive in head first and absorb it, because it's going to serve you for the rest of your life. AC circuits. Also known as how I learned to love complex numbers. All right. So we had these two network components. We had the resistor, so R, where current voltage relation is V over I, and the impedance, which was by definition the voltage phasor over the current phasor. For a resistor is R, and for a capacitor, that's a capacitance. We have C is Q over V, that's in real space, but in complex space, it's 1 over I omega C. And that is also, by definition, the voltage over the current phasor for a capacitor. Okay. Then we had impedance, right? So impedance, it's this physical quantity which is complex, and it's just like before. And then we had series and parallel rules. So series and parallel rules. By the way, I was reviewing my slides from last lecture and I made a couple of typos. So I updated the notes. Okay, so series and parallel rules. So series, we have, if they're in series, then the voltages add, but now instead of voltage in real form, we use the voltage in phasor form. The currents are the same. And therefore the impedances, add. And in parallel, the voltages are the same. So the voltage across this is V2. But now the currents add up to the total current. And the impedances add inversely. Impedances add inversely. Now, I want to show you now what are the series and parallel rules for capacitors, because we haven't really talked about it yet. So series, let's say we have two capacitors, then so a C1 and a C2, C1 and a C2 in series. Then C12, which would be, Z12 would be Z1 plus Z2, which would be 1 over I omega C1 plus 1 over I omega C2. And that we could equate with an effective impedance, which is what we always do. And then that would be equal to this, which means that for capacitors, if they're in series, the capacitance adds inversely, right? Because it's 1 over C1, 1 over C2, because you can divide these out. So for capacitors in series, they add inversely. Now, for capacitors in parallel, oops. So we could do the same thing. We have a Z12 to the power minus 1 is Z1 minus 1 plus Z2 minus 1. Okay, now the inverse of the impedance of a capacitor is I omega C1 plus I omega C2. And that would be equal to a new impedance that we invert, I omega C12. So again, we can divide out these. So we get, let me write it here because I did that for the other one too. C1 plus C2. Okay, so that's parallel capacitors. And that's series capacitors. Now, you see they do the exact opposite. They do the exact opposite of resistors, right? Because for resistors in parallel, they are inversely added. And for resistors in series, they are added. So the capacitors do the exact opposite because the impedance goes like 1 over C, right? So the fact that that goes 1 over C causes these two rules to look like exactly the opposite as it does for resistors. But just if you remember that what the impedance of a capacitor is, and you remember that impedances do this just like resistors do, then it should not surprise you that the capacitors do the opposite, because the capacitance impedance goes like 1 over the actual capacitance. Okay, so those are the rules for series and parallel capacitors, which we have not used before. Now, in parallel, this is actually, it's not too hard to imagine why that is, because you know, physically, if you have two capacitors, let's say you have two capacitors, you have one capacitor with a plate here, plate there, and now you have another capacitor with two plates, and you put them right next to each other, then these plates on the top, they're connected together and they increase the surface area that the top electrode sees. And the bottom two electrodes are also in parallel, which increases the surface area that that capacitor sees. So they become bigger because they add the total surface area of the capacitor. So that's a physical way of looking at why this needs to be in parallel. In series, unfortunately, is a little harder to visualize. So we'll leave that one as stated. Okay, that's the story for capacitors. Now, inductors. So for inductors, which schematically we can draw like this. So that's the circuit element. We know that there is an inductance, and the units of the inductance are in Henry, symbol H. And we have the basic rule that, sorry, I'm writing this backwards. L di dt is E. So the EMF that gets generated is related to the rate of change. And remember, this was underneath the hood was this current generates a magnetic field. The time varying flux that therefore this inductor sees is generating an EMF, and that's neatly, compactly written like this. So it's really two Maxwell's equations written in one. Now, what's the phasor form? So this is the real form, right? So in phasor form, we can write the, I want to write it very, very explicitly. So E of t is L di dt, and I'm going to write this explicitly as a time dependence. And now I'm going to go to phasor form. So that means that we can write this as the real part of the EMF phasor, e to the power I omega t, and then L times the ddt of the real part of the current phasor, e to the power I omega t. Now, this is a linear operator, which means we can bring this in. So we can just say this is L times the real part times ddt of I e to the power I omega t. And now this phasor doesn't actually depend on time, although at some point in the history of the inductor, at some point we must have turned this on, but we're looking for quasi-static solution. So take the derivative, we just get L, real part, and then we get I omega, e I omega t. Okay, now I'm going to pull the L in, and now we have the real part of the current phasor times I omega L, e to the power I omega t. And now that means this left-hand side is not changed, so the real part, the EMF phasor. EMF phasor is this one. Now, the EMF phasor is just a voltage. So I'm going to take these two parts and I'm going to rewrite them. I'm going to say this is the voltage phasor across the inductor. And this is the current phasor across the inductor. So if it holds for the real part, then there's really no reason to assume that it doesn't hold for the arguments. So this is going to be I, and that is the current that runs through the inductor, I omega L. So therefore, the impedance of an inductor is the voltage phasor over the current phasor is I omega L. There you go. And now we have the basic building blocks. We have capacitor. Z of C is 1 over I omega C. It is a minus I over omega C if you bring the I over to the top, but people usually get tired of writing the minuses, but it's important to realize that there's a minus here. Let me remind you that because I squared is minus 1, that means that 1 over I is minus I. Okay. The brightness dynamically adjusted. All right, yeah, that's not great over there. Okay. Yeah, all right, I don't have to do. So that's for capacitor, and we have the resistor. Z of R is R. And now finally the inductor. Is I omega L. We haven't actually done this analysis in a graphical manner. So let me show you what I mean by that. So if we have a network, this is number 2. Let's say we have a resistor and a capacitor, then we know that the total impedance, ZRC, is going to be R plus I omega C. All right, so the impedance is add, and therefore also the voltage phasors add. So it's the V of R plus the V of C, and that's the current phasor times R, and for a series network, it's the current phasor times minus I over omega C. So therefore, we can draw this, because it's a complex quantity, we can say this is the real axis, and this is the imaginary axis, and this is the complex plane. Then we can draw the voltage phasor for the resistor. We can draw this as a complex number that is pointing in this direction. So that's the voltage phasor. And the voltage phasor for the capacitor is pointing in the minus I direction. So it's pointing in this direction. So this is VC, and this is VR. And therefore, because they're added, we can add them just like vectors. We can add the one to the other, and we get V of RC here. Okay. Now, if they're like this, and we measure the voltage across the capacitor, we measure the voltage across the resistor, is not going to change the relation between VR and VC. So VC is lagging behind the current, right? Because it's behind the current phasor. And this is the graphic way of looking at the same thing. So imaginary plane. Now let's do this for a resistor and an inductor. And by the way, I made this comment before, but some people draw resistors like this. But I think that's confusing, because if you start drawing these circuit diagrams faster, then at some point these are going to look very much the same. But just so you know, so that's our resistor, that's our inductor, that's our resistor, that's our capacitor. Now, if they're ZRL, it's R plus I omega L, and the voltage phasor is the current phasor, R plus current phasor I omega L. So that means in the complex plane, where this is real and this is imaginary, the resistor is still doing this. This is V of R. And now our inductor is leading the current, so it's pointing up because it's in the positive, it's in the positive direction. Now that's resistor, capacitor, and if they're in parallel, it's a little harder to visualize because you have to take the inverse of the phasor. So then this would become still a real thing, but with a unit of 1/volt. This would also be still an imaginary object, but in 1/volts, but it would be pointing in the opposite direction. Those are a little harder to visualize, but it usually just means that you flip it from positive imaginary to negative imaginary and vice versa. Okay, now this is the nice one, the really interesting one. This is one of my favorite things. Okay, this is the inductor and this is the capacitor. So Z, LC is, it's the I omega C plus, sorry, 1/I omega C. And in fact, I did this wrong here as well. And where was I? Oh yeah, I omega L. So this is the impedance of the inductor, this is the capacitor. Now, I will write the voltage phasor. So the voltage phasor, LC, is the, it's I times minus I over omega C plus I omega L. All right, so in the complex plane, the capacitor is down. I'm drawing it right next to the imaginary axis because otherwise it's a little hard to see. And that's down, and this one's up. Now, you see, one points up, the other points down, which means that if you add them together, it's going to be pointing either up or down, or for a very special case, they'll be exactly equal. And there's a special case, and we're going to, when VLC is 0, it's 0 when this term and this term added together add up to 0. That means that either the current phasor is 0, but we're not doing that. That's not playing the game. Or this is equal to that. So we have a, minus I over omega C plus, this is our I omega L, is 0. That means that, so divide the i's out and bring this one over to the other side. And now you have an omega, 1 over omega C here and an omega L on the other side. So you get omega L is omega C inverse. So multiply by both and divide by LC. And this is omega naught is 1 over the square root of LC. This is called the resonant frequency. So there is at lower frequencies. So let's look at how this happens. So at low frequencies, below this resonant frequency, the impedance of the capacitor would be bigger than the impedance of the inductor, right? Because this one is bigger at lower frequencies. In other words, the voltage phasor of the capacitor would be bigger than the voltage phasor of the inductor. So at low frequency, this one is way bigger than this one, right? Now, frequency increases, two things happen. frequency increases, this one goes up, this one goes down. So this one becomes bigger, and this one becomes smaller. And then when you have resonance, they're exactly equal. I don't have enough space. they're exactly equal. So therefore they cancel exactly. And then afterwards, when you keep going up in frequency, the impedance of the inductor keeps going up, and then this one keeps going down. So now we're over here. So this impedance is in the negative imaginary axis below the resonance. It's exactly 0, and then positive imaginary axis when it's at 0. Now, this kind of resonator is used a lot in circuits. In radios, for instance, they're used to tune resonant circuits to tune into certain frequencies. Even though sometimes they do this in digital domain, yet still a lot of times when people have antennas that they want to tune to very specific frequency, what you could do is you could have an inductor and you could have a capacitor that you could vary. And then when you change the capacitance, you change the resonant frequency. So you pick up a certain frequency because the impedance is 0, goes through it, and you can use that to select radio stations or what have you. So we've done the most simple series circuit setups, and now let's start looking at filters. All right. Filters. So remember when we started first, we had this filter that we had analyzed, and we were measuring the voltage across the capacitor as a function of the AC signal and frequency that we were applying to the resistor and capacitor in parallel. And I said, this is a low pass filter. And I said, well, it's a low pass filter because low frequencies, this thing is passing, and at high frequencies, it's not working. So this is a low pass filter, but now I'm gonna draw this a little bit differently. So I'm gonna draw this in the following manner. So I'll put the resistor here, and I'll put the capacitor here. And I'll say that the input is here. This is V in, and the output is here. Oops. So it's very much the same as this. I just moved the capacitor to the side, and I flipped the resistor over, and gravity doesn't do much with electrons. So this is the same circuit, but now we're really describing it as something that takes something on the input and makes it show up on the output. And we already know what the ratio between the V of C to the V of RC was, but in the context of filters, we actually always use this object called the transfer function. So I'm going to write this down. Transfer function, and that transfer function is h of omega, and it is by definition the output phasor over the input phasor. And so it's a dimensionless thing, right? Because this one is in volts, this one is in volts too, and this itself is not a phasor, right? Because these are two phasors, and then afterwards the phasor nature is divided out. But this just describes how much of the input comes out on the output. So we already know what that is. So V out is the voltage developed across this capacitor. So that's I times 1 over I omega C, and the input is divided over both, so R plus 1 over I omega C, and therefore that is, so multiply everything by 1 over I omega C, divide out the I's, so done, you get 1 plus I omega RC minus 1. So this is the transfer function of this filter. And this is a low-pass filter because when we take the limit of omega to 0 of h, it is 1, right? Stick 1 in here, you get 1. And if you take the limit of omega going to infinity of this transfer function, it is 0. So therefore, this is a low-pass filter, or a low-pass filter LP. Okay, so that's how you identify it. You say, okay, this is 1 or 0. And the characteristic frequency, so the characteristic frequency is the frequency that describes sort of in between low frequency and high frequency. So in other words, the frequency that separates that part from passing from the part from blocking. So it's usually found by solving this equation, and that is this absolute value of the transfer function is the absolute value, and I showed you this trick before, so that's the absolute value of the square root. I showed you this trick last lecture. Remember that the absolute value of 1 over r ei phi is 1 over r. That went in there. So solving this for 1 over root 2 means invert it, square it, you get 1 plus omega squared RC squared, 2 subtract 1, so you get omega squared RC squared is 1. Omega is 1 over RC. Okay, this is the characteristic frequency, this omega naught. So we're going to call this omega naught, and that's this one. And that's the frequency at which we have this crossover. So for instance, another way to write this is to have not omega itself go to 0, but omega in relation to omega naught. And omega in relation to omega naught. That's a little bit nicer to write it this way because this sounds too absolutist. Okay. So this transfer function we can draw. It's usually the it's usually a 2 plots. It's the absolute value versus frequency. So this is low pass, so it starts here at 1, and then there's this point here, omega naught, where it goes through 1 over root 2, so that's 1 over root 2, that's here, and then afterwards it goes to 0. So that's something like this. So okay, so that's the transfer function. So we're saying it's blocked, and this is passed. Now you see this transition is not very sharp, so we can say anything below omega naught is passed, but that's not really true because there's still stuff that's being attenuated if you get close to this. And then also, if you're right above that frequency, you could say, well, this is blocked, but it's really not. I mean, it's attenuated, but not by much. So if you use one of these filters, you usually want to make sure that if you have something big that you want to filter out or big that you want to keep, you make sure that you keep these frequencies far apart, because otherwise it doesn't work very well. So there are filters that have a transition that is sharper, but unfortunately you cannot get a transition that is infinitely sharp. So that's an entire course in itself. So, but because this low frequency is passed and high frequency is blocked, we're going to say this is therefore a low pass filter. Okay. Now, the argument. So the phase difference, also important. So the argument of H is the argument of 1 plus I omega R C to the power minus 1 is minus the argument of 1 plus I omega R C. And this is using that same trick where the argument of 1 over R E I phi is minus phi. Okay, and that is the arctangent of the imaginary part over the real part, omega RC, with a minus sign. Okay, so it starts off here. So arctangent, it's always negative. At low frequencies, it's 0. Then it goes through, when you are at the critical frequency, it's the arctangent of 1. So arctangent of 1 is, I believe it's pi over 2. I'll check it in a second. Pi over 2. No, 4. Pi over 4. So that's at this frequency, omega naught. And then in the end, we end up at pi over 2. So sorry, this is a pi over 4. Okay, pi over 4, pi over 2. So let me draw that. So it goes like this. So when this thing is passing, it's not really causing too much of a phase delay between the input and the output. But when it's blocking, it's going to be pretty much out of phase. And that's how we quantify filters. So I went super long because this is the first time that you're seeing it. But in the end, when you start seeing these filters more often, and you will see them more often because we're going to do a bunch of them, you'll start seeing more quickly what these things are supposed to do. Now we're going to do the transpose. So we're going to do the transpose. So we're taking the same input, but now I'm swapping the resistor and the capacitor. And the output phasor is still here. And the input phasor is here. There's an important thing that I forgot to tell you, by the way. This current that goes through here is only the same as the current that goes through here if whatever you're attaching here is not taking any current. So usually if you have an oscilloscope, it's going to have a high impedance input. It's not going to take too much current, so that's okay. But if not, then you have to solve what happens if you have an extra impedance here in parallel with the capacitor. But these are the most simple filters, so we'll assume that. Okay, so assume V out is not sinking current into whatever you're connecting to it. All right, now here we go. Calculate H omega for this filter. remember the transfer function is the output phasor over the input phasor, and the current that runs through the capacitor is the same as the current that runs through the resistor, because the assumption is that V out is not sinking any current. No power is delivered to V out. So therefore, IC is IR, is IRC, because then they're in series. So V in is therefore, because there's no power delivered, these currents are the same. And that means that the input voltage, which is applied between these 2 points on the circuit, drives a current through this network in this direction. No current goes this way. So the current that goes through the capacitor is the same as the current that goes through the resistor. So they're in series. So therefore, currents are the same, and the voltage is split between the two. So the voltage that develops across the capacitor is the voltage phasor across the capacitor is Ohm's law, just IC/ZC. This is Ohm's law, regular Ohm's law. And because the currents are the same, you can factor that current out. And now V out over V in, the currents, they drop out, and then you get R, 1 over I omega C plus R, and then you factor it out. And this is, let's see, so limit omega going to 0 of H. Okay, now take omega going to 0, so you get 1 over omega here, that's goes to infinity, so you get 1 over infinity, that's 0, so this is 0. The limit of omega going to infinity is, well, so 1 over infinity, that is, so 1 over infinity is 0, so 1 over 1 plus 0, that's 1. So this does the exact opposite of what we had before, so this is a high pass filter. And we could do the same thing. We can do that plot of this. This is 1 plus 1 over omega squared, R squared, C squared, minus 1. And the argument, the phase difference, is minus the arctangent of the imaginary part. The imaginary part is minus because there's a 1 here. So I'm going to draw that explicitly here. So I'm going to move the I up so I don't get questions anymore of why there's a minus here. Okay, minus I. Then it's minus the arctangent of the number in the denominator. And that's the arctangent of the imaginary part over the real part. So the imaginary part is minus 1 over omega RC. Real part's 1. So you get 1 over omega RC. And the characteristic frequency is where H is 1 over root 2. And when you solve it, you see that, oops, minus 1/2. when you solve it, you'll see that this term again needs to be 2. That means that this term needs to be 1. That means that omega squared r squared c squared needs to be 1. And that's the exact same condition that we had before. So it's omega naught is 1 over RC. So this circuit does the exact opposite. So the phase, there was a minus and a minus. Sorry, the minus and the minus, these cancel. So that becomes a plus. So this phase at 0 frequency is large, right? So that starts out here, pi over 4, 2. And then when omega goes to infinity, this thing is 0, and arctangent of 0 is 0. So this does something like this. And the transfer function starts at 0 and then goes to 1. And this point, 1 over root 2, where this is 1, is the characteristic frequency. Characteristic frequency. So it does the exact opposite of this one. Phase is inverted, but also this one passed low, this one passes high. This one blocks high, this one blocks low. So these, as I was just explaining, these filters are usually the simplest one that you can use, where you always assume that whatever you're presenting this output signal to is not going to take any current. So oscilloscopes have high input impedances, multimeters have high input impedances. This is actually, it's a very, very common thing to do in network theory, where, for instance, if you have a bunch of sources and a bunch of networks, you do this thing called impedance bridging, where your source is a low output impedance thing, like a battery, and your detector is a high input impedance thing, like an oscilloscope. And it just makes life a lot easier if you do it this way. So that's the common way that low frequency filters are used. So these are AC filters, but they're low frequency AC filters. If you go to higher frequencies, it becomes an entirely different matter. You have to consider their waveguides here, and then actually what you do is you design it such that you can deliver this power to a load of 50 ohms. But that's an entire course unto itself. So that's the transpose. So you saw that what we did, all we did was we swapped these two, right? So we took the resistor and the capacitor, we swapped them, the capacitor and resistor, swap them, and then it went from low pass to high pass, or vice versa. Now, hopefully you have seen that we keep repeating ourselves when we do this filter. So there's actually a bunch of stuff that we can say in the abstract sense about these types of impedance bridging filters. So the grand unified filter theory for bridging, impedance bridging. Okay, the most simple filter, and it's the one that we will always often see, consists of this kind of a configuration, where now I'm not saying these are resistors, but I'm calling this impedances. So there's a Z1, and then there's a Z2. And we measure here, and then we present the signal here. And then we always say no power to V out, because again, that's what we do with impedance bridging. So therefore, I1 is I2 is I12. Vn is applied to both. So it's the current phasor, and these are in series, and V out is developed across that output impedance. which in this case is Z2. So therefore, the transfer function is this over that. So Z2 over Z1 plus Z2. And then we can divide out our Z2, and we get 1 plus Z1 over Z2 to the power minus 1. So this is the general transfer function, for filters of this sort. So now that we have this developed, it's super easy to see what happens with this filter. So with this filter, we have resistor capacitor. So Z2 is 1 over I omega C, and Z1 is R. Okay, Z2 is 1 over omega C, I omega C, and Z1 is R. So you get 1 plus I omega RC inverse. Yeah, 1 plus I omega RC inverse. Done. This one, you do the same thing. Now, the capacitor and the resistor are reversed. So our Z1 is the capacitor, our Z2 is the resistor. So Z1 is the capacitor, Z2 is the resistor. So we get 1 plus Z1, which is 1 over I omega C. So we have 1 plus 1 over I omega C divided by R. So it's 1 plus 1 over I omega RC. Yeah, here we go. 1 over 1 plus 1 over I omega C, and I move the I over to the other side. So you see, because we're always doing the same thing, we might as well do that work up front. So this is way easier. So now we can do this for, because it doesn't really make much sense to keep repeating the thing. So we can talk about a couple of filters. So for instance, we haven't done filters with inductors yet. So this is the out. And at some point, usually we stop drawing the input and the output because, you know, it's assumed that we set up these things from left to right. So that's all, and that's R. So our transfer function is, well, okay, it's 1 over 1 plus Z1 over Z2. So Z1 is I omega L, and that's R. Done. Okay, what kind of filter is this? Well, if you take the limit of omega to 0, now omega goes to 0, 1 plus 0 inverse is 1. So it's 1, and the limit of omega going to infinity is, well, take this thing to infinity, because 1 plus infinity is infinity, inverse of infinity is 0. 0. So this is no pass. All right, take the transpose. We get transpose. We get the we get 1 plus Z1 over Z2. Z1 is the resistor, and Z2 is the inductor, I omega L, minus 1. This does the reverse. So I'm going to, instead of writing the limits, it just does high pass filter. You should see it now, right? So now compare this to the transfer functions with the capacitances. So when we had this filter versus this filter, we had a resistor, and then here we had a capacitor, and we had an inductor. Now, this is a high pass filter, but this one was a low pass filter. And why is that? Well, it's the same thing that we were saying before. It's because the impedance of an inductor and the impedance of a capacitor have the exact opposite behavior. So the transfer function of this looks actually like the transfer function of this, because the inductor and the capacitor are inverted. So most of the time, if you want to build a filter and it doesn't work with a capacitor, you can usually just swap the components and swap the capacitor for an inductor. Okay, now the characteristic frequency for these kind of circuits, characteristic frequency, is still where this transfer function is 1 over root 2. Okay, well, let's do this one. It doesn't really matter because you can kind of see what's going to happen here. We're going to get a 1 over root of real squared plus imaginary squared. For the high pass filter, it's R over omega L squared, and that then needs to be 1. And for the low pass filter, it's omega L over R, and that needs to be 1. And obviously 1 over 1 is 1. So this filter and this filter will have the same characteristic frequencies. And it's where R over omega L is 1. Let me draw this as an actual L. And therefore, omega is R over L. That's for an RL filter. Now, there are 2 more things I want to talk about today. It shouldn't take you too long. The first is there an intuitive way to see whether something is a low pass or is a high pass filter? And there is. So without having to calculate the transfer function. So there is a shortcut. There's a shortcut to a shortcut to a shortcut. Okay, so in this case, if you look at the diagram directly and you consider the 2 limiting cases, really low frequency, really high frequency. Okay, first, really low frequency, remember the impedance here is I omega L. Really low frequency, this thing has an impedance of 0. So that means that all of the signal comes through here. So limit of omega goes to 0 of the transfer function is going to be 1 because it's just a wire. So if you draw it, it will be this filter. So it will be a low pass filter. So that's the low frequency picture of the network. Okay, now the high frequency picture, in high frequency limit, this impedance goes to infinity, so it becomes an open circuit. So there's nothing here. So therefore the of H is 0, right? Because at high frequencies, this thing is just an open circuit. So there's nothing that can go through here. The current can't go through. So if you see this, you should see, hey, by the way, at low frequencies is a wire, everything's going to come through. Therefore, this is a low pass filter. And you don't even need to calculate the characteristic transfer functions and everything. The only thing you want to make sure that you pay attention to is the crossover frequency. So similar with this. So for instance, in the low frequency limit, this is a wire, and that means that the output voltage is shorted. So limit omega to 0, it's just a resistor with a wire. So ideal wire doesn't allow any voltage to exist between 2 points on a wire. So therefore, that it is 0. And now the high frequency go like this. And now in the high frequency limit, this thing is an open circuit. So therefore, nothing goes through here. So all the current that goes through here goes through here. And that, of course, kind of violates our assumption that we're not going to deliver any current, but let's be quiet about that and not tell anybody. So therefore, this is a high pass. Okay, what does that look like for capacitors? Well, we do the same thing. So capacitor, resistor. So the low frequency representation of representation of a capacitor is just an open circuit, because that is physically what it is. It's just two metals that are separated by, or two conductors that are separated by an insulating region. If it's insulating, can't get any current to go through. It's not until you go to finite frequencies that you're allowed to do that. So the low frequency picture of this is the aforementioned open circuit. So that is 0. The high frequency impedance, frequency goes to infinity. It's 1 over infinity is 0. So that's just a wire and a resistor. And that means you get 1. So that's a high pass filter. So HPF, LPF, high pass filter, obviously. High pass filter. And this is low pass filter. Okay, last permutation. All right. Low frequency limit. It looks like this. Now the capacitor is here between these 2 points, and there's nothing going. So this means everything goes through. That's a dead short. So nothing comes through. So this is low pass filter. And now you've got the 4 different versions of RC and RL circuits. And again, you see that if you swap out the resistor for capacitor, you go from high pass to low pass. Or here, resistor to capacitor, you go from high pass to low pass. And if you take the transpose, you go from low pass to high pass, transpose, low pass to high pass. So hopefully you have a pretty good idea of how these filters look. Now, these are filters that are the most simple linear filters. So for instance, what we have not done yet is build a filter where we can use both an inductor and a capacitor. And when we use both, we will get resonance phenomena. And these are not the simple low pass and high pass filter, but these are going to be band pass or band stop filters. And I will talk about that in next class. Now, as I was saying, these filters, you find them everywhere, not only in the lab, but also in all the devices that you might have. There's resistors, capacitors, and inductors everywhere, and most of the time they're trying to filter stuff. For instance, if you have a transformer and you're trying to convert the AC signal on the that comes from the outlet to a low voltage DC signal, then what you can do is you can flip it over, make sure that it's going in one direction, but then you still have some 60 Hertz ripple, and you usually get rid of that with a low pass filter, so it kind of smooths it out. If you have for instance, if you live right next to a rail car, that sometimes it messes with the ground signal on the circuit. So sometimes you want to decouple your equipment from the line power. So you will set it up with a high pass filter. So there are all sorts of things that you can use for using these filters. There's actually a famous example. This is something that I was kind of an eye-opening moment for me when I learned about this. So when we do circuit theory or when we do AC circuits, we always say, okay, we have some, we've got some resistor and we've got some capacitor, and where is my resistor, my capacitor? So there's my resistor, my capacitor, and you put this resistor in a network, you put a capacitor in a network, and then that's it. But what you need to realize is that what a capacitor fundamentally is just two conductors separated by an insulating region, or even more generalized, you could say it's two conductors that have a voltage in between. And even if you don't plan for capacitance to be present in your circuit, you might very well still have it. So a very famous example was in early telephony, where we still had analog telephones. There was this thing where if you put the receiver on the hook, right? You put the receiver on the hook, it would open a contact such that there was no more there was no more signal that could run through the telephone. But as you now know, something like this, two conductors that, even though they're separated by some kind of a insulating gap, that still constitutes a capacitance. So people cleverly figured out that if you query an old school analog telephone at high frequencies, you can actually listen in on conversations in the room. So just because at high frequencies, this thing doesn't appear as a switch that's open anymore. So there's a lesson in there somewhere where you if you sorry, if you walk around and you pick up charge from one point to the other, and you discharge yourself, you are also changing your capacitance to the rest of the world. So you walking around just changes what circuits around you see. It's once you start thinking about the fact that AC circuits and DC circuits are not just about circuit elements, but they really are a very neat, compact way of describing how conducting things can interact when they're arranged in a three-dimensional manner in the real world. And once you have a circuit diagram representation of that, that is super, super useful. For instance, another example is in electrochemistry. So if you have a conducting material that you stick in some kind of a ionic solvent, there is a potential difference that develops, and as a result of that potential difference, there's a capacitance that develops. So in your electrochemical setup, there's going to be capacitance, and then the ionic liquid is like a resistor, so that's an RC circuit. So just because you didn't put in a resistor and a capacitor doesn't mean that it doesn't behave like a resistor and a capacitor. So, but it's useful to then be able to abstract it to resistor and capacitor circuits, and you'll be able to understand the world around you much better because you now have a solid understanding of how these things work.